If gravity emerges from information, then what is information itself? And if information lies beneath gravity, then what lies beneath information? What is reality actually made of? For more than 2,000 years, that single question has driven some of humanity's greatest discovery. It's inspired philosophers, challenged scientists, and pushed us to build machines powerful enough to peer into the smallest corners of existence. Every generation believed it had finally reached the foundation of reality. Every generation was wrong, and today, after centuries of discovery, physics has arrived at a place stranger than anyone could have imagined. In the last episode, we uncovered a remarkable possibility. Gravity, the force that shapes stars, galaxies, and the structure of the cosmos, might not be fundamental at all. It may emerge from something deeper, from entropy, from information, from the way reality organizes itself. But that discovery opened an even deeper mystery. If gravity emerges from information, then what is information made of? Is information the true foundation of reality? Or is there another hidden layer beneath it? Does reality eventually reach a final building block, or does every answer simply reveal another question waiting underneath? Surprisingly, this isn't a modern mystery. It's one humanity has been asking for thousands of years. More than 2,000 years ago in ancient Greece, philosophers looked at the world around them and asked a deceptively simple question. If you break something apart, what remains? Imagine holding a piece of stone. Break it in half, then break those pieces again. Keep dividing it over and over. Could that process continue forever? Or would you eventually reach something so small that it could never be divided again? Two philosophers, Leucippus and Democritus, believed it would. They imagined tiny, indivisible building blocks that formed everything in existence. They called them atoms, not because they had seen them, not because they had evidence, but because reason alone suggested reality must eventually have a foundation. It was an astonishing idea, and for more than 2,000 years, no one could prove whether they were right. Then, in the early 19th century, science finally caught up with philosophy. John Dalton showed that matter is indeed composed of atoms: gold, iron, carbon, oxygen. Every substance around us is built from different combinations of these tiny building blocks. For a moment, it seemed the mystery had finally been solved. Reality was made of atoms. The search was over. Except it wasn't. Near the end of the 19th century, J.J. Thomson discovered something hidden inside the atom itself: the electron. Suddenly, atoms were no longer indivisible. The very thing believed to be the ultimate foundation contained something even smaller. So physicists looked deeper. Ernest Rutherford revealed the dense atomic nucleus hidden at the atom's center. Niels Bohr explained how electrons occupy quantized orbits around it. Marie Curie's work on radioactivity revealed that atoms weren't nearly as stable or simple as anyone had imagined. The deeper scientists looked, the more complexity they discovered. Then came another surprise. Protons and neutrons, the particles inside the nucleus, also turned out not to be fundamental. In the 1960s, particle accelerators smashed them together at extraordinary energies. And inside, scientists discovered quarks, tiny particles bound together by gluons. Soon the list kept growing. Photons, neutrinos, muons, bosons. An entire hidden world of particles emerged beneath ordinary matter. Instead of finding one final building block, physics uncovered layer after layer after layer. At first, this seemed disappointing. Every answer only produced another question. But then something remarkable happened. Physicists like Murray Gell-Mann began noticing that this growing collection of particles wasn't random. Hidden beneath the apparent chaos was an elegant mathematical order. Different particles belonged to different families. They obeyed precise symmetries. They followed predictable patterns. Eventually, these relationships became one of the greatest achievements in modern science, the Standard Model. It didn't simply list particles. It revealed the underlying architecture connecting them all. Even more astonishing, the theory predicted entirely new particles years before experiments confirmed they existed. Time after time, nature agreed with the mathematics. Today, the Standard Model remains one of the most successful scientific theories ever created. Thousands of experiments have tested it, and every major prediction has been confirmed with extraordinary precision. But despite its incredible success, the deepest question never disappeared. The Standard Model explains how fundamental particles behave. It explains how they interact. It predicts what they should do. But it never tells us what they actually are, or what, if anything, they're ultimately made of. And that realization would lead physicists toward one of the strangest discoveries in the history of science, because what they found next challenged not only matter, but reality itself, eh? Because what physicists discovered next overturned one of the oldest assumptions in science. Particles aren't really particles, at least not in the way we've always imagined them. When most of us picture a particle, we imagine a tiny solid object, a microscopic ball of matter moving through empty space. But quantum physics paints a completely different picture. According to quantum field theory, the framework that underlies the Standard Model, the universe isn't filled with tiny objects. It's filled with fields. Invisible quantum fields stretch across the entire universe. An electron field, a photon field, a quark field, fields that exist everywhere, even in the emptiest regions of space. What we call a particle is simply a ripple traveling through one of those fields. Think about standing beside a calm ocean. The ocean exists whether or not there are waves. A wave isn't separate from the ocean. It's simply the ocean moving in a particular way. Quantum fields work much the same way. The field is fundamental. The particle is only a temporary disturbance within it. An electron isn't a tiny marble racing through space. It's a localized vibration in the electron field. A photon isn't a little packet of light flying across the universe. It's an excitation of the electromagnetic field. Everything we once believed was made of particles is actually made from invisible fields. For a moment, it seemed the mystery had finally been solved again. Reality isn't made of atoms. It isn't even made of particles. Reality is made of quantum field. But history has taught physics one painful lesson. Whenever we believe we've reached the bottom, reality surprises us again, because another question immediately appeared. If fields are fundamental, what are fields made of? Physicists searched for an answer, and they found themselves returning to one of the most famous equations ever written, E equals mc squared. Einstein's extraordinary insight reveals something astonishing. Matter and energy are not separate things. They're different expressions of the same underlying reality. Mass can become energy. Energy can become mass. Stars perform this transformation every second. Inside their cores, matter becomes light. Energy becomes new particles. The universe constantly converts one into the other. Perhaps then, reality isn't made of matter at all. Perhaps everything is ultimately made of energy. For a while, that seemed like the final answer, until physicists asked one more uncomfortable question. What exactly is energy? Unlike a particle, you can't hold energy. Unlike a field, you can't point to it. Energy isn't an object, it's a description. It tells us how much change is possible, how much work can be done, and how a physical system is arranged. In other words, energy doesn't describe what something is, it describes information about its state. And that subtle distinction changed everything. Because once information entered the picture, physics began moving in a completely different direction. Near the end of the 20th century, one physicist became fascinated by this idea more than anyone else, John Archibald Wheeler, a brilliant theoretical physicist, a colleague of Albert Einstein, a mentor to Richard Feynman, one of the greatest scientific minds of the modern era. After spending an entire lifetime studying reality, Wheeler reached an extraordinary conclusion. Quantum mechanics seem to be pointing towards something unexpected. Before a measurement takes place, a particle doesn't possess a definite position, or a definite momentum, or even a definite state. Instead, reality is described by a wave function. And what does a wave function actually contain? Information. Not certainty, not physical objects and ID, but information about every possible outcome. Then something remarkable happens. A measurement is made. One possibility becomes real. The wave function appears to collapse. Possibilities become facts. Uncertainty becomes knowledge. Wheeler couldn't stop asking himself a deceptively simple question. If the only thing that exists before measurement is information, then why do we assume matter is more fundamental? What if we've been looking at reality upside down? What if matter doesn't create information? What if information creates matter? That single idea became one of the most famous phrases in theoretical physics. It from bit. Every physical object, every particle, every atom, every galaxy, every star, every human being, every it could ultimately arise from bits, from distinctions, from yes or no, from the most fundamental units of information imaginable. At first, many physicists dismissed the idea as little more than philosophy, elegant, creative, but impossible to prove. Then something happened that forced the scientific community to take Wheeler's proposal far more seriously. Black holes, the most mysterious objects in the universe, were about to reveal something that no one expected. And what they revealed would forever change the way physicists think about information. Black holes have a way of exposing the deepest flaws in our understanding of reality. Whenever physicists think they finally built a complete picture of the universe, a black hole comes along and breaks it. In the 1970s, Stephen Hawking made one of the most astonishing discoveries in modern science. Until then, black holes were believed to be completely black. Nothing could escape them. Not matter, not light, not even information. But Hawking showed that this wasn't entirely true. Using quantum mechanics, he discovered that black holes slowly emit radiation. Today, we call it Hawking radiation. And over unimaginable lengths of time, that radiation causes black holes to evaporate. Eventually, a black hole can disappear completely. At first, this seemed like an extraordinary breakthrough, but almost immediately, it created one of the greatest crises in theoretical physics. Imagine throwing an entire library into a black hole. Every book, every page, every word ever written. If the black hole eventually evaporates, what happens to all that information? Does it vanish forever? If the answer is yes, then one of the most fundamental principles in quantum physics is wrong. Because quantum mechanics tells us something extraordinary. Information cannot simply disappear. It can change form. It can become incredibly difficult to recover, but it cannot be destroyed. Suddenly, physics faced an impossible contradiction. General relativity suggested one answer. Quantum mechanics demanded another. Both theories had been tested with incredible precision. Both had succeeded everywhere we looked. And yet, inside a black hole, they could not both be right. This became known as the black hole information paradox. For decades, some of the world's greatest physicists argued over a single question. Where does the information go? Does it escape somehow? Does it remain hidden forever? Or does reality preserve it in a way we've yet to understand? The debate continues today, but along the way, physicists noticed something even stranger. Jacob Bekenstein discovered that a black hole's entropy doesn't depend on its volume. It depends only on the area of its surface. That sounds like a small mathematical detail. It isn't. It's one of the most profound discoveries in modern physics. Think about it. If every piece of information inside a black hole can be described entirely by its surface, and then perhaps volume isn't as fundamental as we thought. Perhaps three-dimensional space is only an appearance. Perhaps the information describing an entire region of space can exist on a two-dimensional boundary. At first, the idea sounded absurd, but the mathematics refused to let it go, again and again. Different calculations kept arriving at the same conclusion. Eventually, this became known as the holographic principle. Imagine standing in front of a hologram. The surface is completely flat, yet somehow, it creates the convincing illusion of depth, a three-dimensional world emerging from two-dimensional information. Now imagine something even more extraordinary. What if our universe works the same way? What if everything you've ever experienced, every galaxy, every planet, every atom, every moment of your life, is ultimately encoded as information on a distant two-dimensional boundary of reality? It sounds like science fiction, yet some of the most sophisticated mathematics and theoretical physics points in exactly that direction. No one has proven that our universe is literally a hologram, but the possibility has become impossible to ignore. Then another revolution arrived. Quantum computers, unlike ordinary computers, which process information one bit at a time, quantum computers use qubits. A classical bit can exist in only one of two states, 0 or 1. A qubit is fundamentally different. Because of quantum superposition, it can exist in multiple possibilities at once until measurement occurs. That single difference changes everything. As more qubits become entangled, the number of possible states grows explosively. A quantum computer containing only a few hundred qubits can, in principle, represent more possible configurations than there are atoms in the observable universe. That number is almost impossible to imagine, and yet quantum computers are real. They already exist. They're not perfect, They're not yet replacing classical computers, but they demonstrate something extraordinary. Information behaves according to the strange rules of quantum mechanics, not classical intuition. And that raises a fascinating possibility. Perhaps the universe itself processes information in exactly this way. Perhaps reality doesn't simply contain information. Perhaps reality computes information. Some physicists have even wondered whether every quantum interaction resembles a tiny computation, a continual process of possibilities evolving into definite outcomes. It's an intriguing idea, but it remains exactly that, an idea, not established fact. Still, the deeper researchers explore quantum information, the more surprising its properties become. Information can be entangled across enormous distances. It can be transferred using quantum teleportation. It follows mathematical laws unlike anything found in classical physics. The more we investigate, the less information looks like a tool we've invented to describe reality. And the more it begins to look like something woven into reality itself, almost as if the universe isn't built from matter or energy or even space, but from information. Yet even that astonishing possibility leaves us with another question. If information truly is fundamental, why does it obey these laws? Where do those laws come from? And to answer that, physicists have proposed some of the boldest ideas ever imagined, and each of them attempts to explain what lies beneath the deepest layer of reality itself. If information truly sits at the foundation of reality, then one question becomes impossible to avoid. What is information itself made of? This is where modern physics reaches the very edge of human knowledge. Beyond this point, there are no final answers, only remarkable ideas. One of the most ambitious is string theory. Instead of imagining particles as tiny points, string theory proposes something radically different. Everything in the universe is built from unimaginably small, vibrating strings. These strings are so tiny that even our most powerful particle accelerators cannot observe them directly. According to the theory, the difference between an electron and a photon isn't that they're made of different substances. It's that the same fundamental string vibrates in different ways, much like a guitar string can produce many different notes. One fundamental string could create every particle in the universe. Matter, light, force, everything. One of the reasons physicists became so excited about string theory is that gravity appears naturally within its mathematics. For decades, gravity had refused to fit inside quantum mechanics, but string theory seemed to offer a possible bridge between the two, a framework capable of unifying Einstein's relativity with quantum physics. If correct, it would be one of the greatest achievements in scientific history. But there's a challenge. String theory predicts extra dimensions beyond the four we experience, not 5, not 6. In some versions, 11 dimensions. Dimensions that may be curled up so tightly that they're impossible to observe with today's technology. It's an elegant idea. Its mathematics is breathtaking, but elegance alone isn't evidence. So far, no experiment has confirmed that string theory describes our universe. Another approach takes a very different path. It's called loop quantum gravity. Instead of changing the particles, it changes space itself. Einstein described space-time as smooth and continuous, like an endless fabric stretching across the cosmos. Loop quantum gravity suggests something much stranger. Space itself may be built from tiny, indivisible units, not continuous, not infinitely divisible, but woven together from discrete quantum loops. Imagine looking at a piece of fabric from across a room. It appears perfectly smooth, but move closer, closer still. Eventually, individual threads become visible. Loop quantum gravity suggests space may work in much the same way. What appears continuous at everyday scales could actually be woven from unimaginably tiny pieces. And if that's true, then space itself isn't fundamental either. It's constructed, built from something deeper. The remarkable thing is that both string theory and loop quantum gravity begin with completely different assumptions. Yet both arrive at the same destination. Reality appears less like solid matter and more like an underlying mathematical structure. Then there's another possibility, one that's becoming increasingly influential. Perhaps neither strings nor quantum loops are the deepest layer. Perhaps information itself is fundamental. In this view, particles aren't made from strings or loops or tiny pieces of matter. They simply are organized information, different arrangements, different patterns, different relationships, An electron isn't built from something beneath it. It is one particular pattern of quantum information. A photon is another. Every particle, every field, every force could simply be information expressed in different forms. If that's true, then reality resembles a language more than a machine. The universe isn't built from objects. It's built from relationships, from distinctions, from patterns, and from the rules connecting them together. Then there is perhaps the most controversial proposal of all, the simulation hypothesis. The suggestion that our universe might itself be the output of an unimaginably advanced computation. Popular culture often treats this idea as science fiction, but the reason physicists discuss it isn't because they believe we've proven we're living inside a simulation. It's because certain discoveries have raised surprisingly difficult questions. One example comes from the work of physicist James Gate. While studying equations related to supersymmetry and string theory, he discovered mathematical structures resembling error-correcting codes, the same kinds of codes engineers use to detect and repair errors inside modern computers. Does this prove reality is a simulation? No, not even close. Mathematical similarities are not proof, but they are intriguing enough to keep researchers asking new questions. Why would equations describing the universe contain structures that resemble computational logic? Coincidence, a deeper mathematical principle, or something we haven't yet understood? No one knows. And that's precisely what makes this frontier so fascinating. Physics has reached a place where every answer creates even deeper questions. The deeper we look, the more reality begins to resemble mathematics, information, relationships, patterns, rather than tiny pieces of physical substance. And despite the differences, every major attempt to explain the universe seems to keep pointing in the same direction, toward information, toward structure, toward something that cannot be touched, yet somehow gives rise to everything we can touch. But if every road keeps leading toward information, there's one final mystery we still haven't answered. If information is truly fundamental, why does information exist at all? If information truly is the deepest layer of reality, then one question remains. Why does information exist at all? It's a question that pushes physics to its very limits. Not because physicists have stopped asking, but because we've reached the edge of what experiments can currently reveal. Here's what we know with remarkable confidence. The Standard Model works, quantum field theory works, reality. Then one question remains. Why does information exist at all? It's a question that pushes physics to its very limits. Not because physicists have stopped asking, but because we've reached the edge of what experiments can currently reveal. Here's what we know with remarkable confidence. The Standard Model works, quantum field theory works, general relativity works. Again and again, experiments confirm their predictions with extraordinary precision. These theories explain the universe with astonishing accuracy. But explaining how reality behaves isn't the same as explaining why reality exists in the first place. And that's where the deepest mystery begins. Every path we've followed, from atoms to particles to quantum fields to energy to information, has revealed another layer beneath the last. Each discovery has transformed our understanding. Each answer has opened an even deeper question. Now we find ourselves standing at the edge once again. Some physicists believe mathematics is the ultimate foundation. According to this view, the universe doesn't merely obey mathematics. The universe is mathematics. Every particle, every force, every law of nature, every galaxy, every living organism could simply be different expressions of timeless mathematical relationships. Reality wouldn't be built from physical substance. It would be built from pure structure. Others take a different view. They argue that information itself requires an observer. That information only has meaning when something is capable of distinguishing one state from another. From this perspective, a consciousness may play a deeper role than we currently understand, not because physics has proven consciousness is fundamental, but because the relationship between observation and quantum mechanics remains one of science's greatest unanswered questions. Other researchers suggest something even more radical. Perhaps information doesn't come from anything else. Perhaps it is self-consistent, self-generating, a network of relationships requiring no deeper foundation beneath it. Reality simply exists because information exists, and information exists because reality does. A self-contained loop with no beginning and no end. Could that be the final answer? We don't know. And perhaps that's exactly what makes this journey so extraordinary. Science isn't powerful because it already knows every answer. Science is powerful because it keeps asking better questions. The history of physics has never been the story of certainty, and it's been the story of curiosity. Every generation believed it had reached the bottom. Every generation discovered there was another layer waiting below. Perhaps our generation is no different. Perhaps information isn't the end of the story. Perhaps one day another discovery will reveal an even deeper foundation, something we can't yet imagine, something our current mathematics isn't capable of describing. Or perhaps, for the first time in history, we've finally reached the true foundation. We simply don't recognize it yet. Whatever the answer turns out to be, one thing has become impossible to ignore. Information appears everywhere. It's woven into quantum mechanics. It's connected to entropy. It lies at the heart of black hole physics. It shapes modern quantum computing. It appears in our deepest attempts to understand gravity. Again and again, reality keeps pointing back toward the same remarkable idea, not matter, not particles, not even space and time, but information. Still, we must be careful. Physics has not proven that information is the ultimate substance of reality. It has not proven that consciousness creates the universe. It has not proven that we're living inside a simulation. These remain hypotheses, powerful ideas, elegant ideas, ideas supported by intriguing mathematics and ongoing research, but ideas that still await decisive experimental confirmation. That's an important distinction. Because the strength of science has never been certainty, its strength is honesty. It tells us not only what we know, but also what we don't know. And right now, the deepest foundation of reality remains one of the greatest unanswered questions in human history. Perhaps one day we'll discover that everything is mathematics. Perhaps everything is information. Perhaps reality is built from principles we haven't even imagined. Or perhaps the universe will always keep one final mystery beyond our reach. And maybe that's exactly what inspires us to keep exploring, to keep questioning, to keep looking beyond the horizon of current knowledge. After thousands of years of inquiry, after countless experiments, after revolutions in physics that completely reshaped our understanding of existence, we arrive at a surprisingly humble conclusion. We know more than any civilization before us, yet we still don't know what reality is ultimately made of. And maybe that's the most beautiful discovery of all, because every mystery we've solved has led us to an even greater mystery. The deeper we look, the more extraordinary the universe becomes. Perhaps reality isn't something we've been placed inside. Perhaps it's a question we're slowly learning how to ask. And every experiment, every equation, every observation brings us one step closer, not to the end of the mystery, but to a deeper understanding of how extraordinary that mystery truly is. And now, one final question remains. If information shapes reality, what shapes time? We've treated time as though it flows, as though the past disappears, the present exists, and the future is yet to arrive. But what if that's only how reality appears from our perspective? What if every moment in history already exists? What if yesterday, today, and tomorrow are all equally real? What if the passage of time is something your mind creates rather than something the universe experiences? Some of the most profound ideas in modern physics suggest exactly that. Next time, we explore one of the most unsettling possibilities science has ever proposed. Not that time moves differently than we think, but that time may not move at all. What if the entire history of the universe already exists? Every beginning, every ending, every choice, every possibility, all at once. Join us in the next episode of Beyond Physics as we ask a question that could completely transform the way you understand existence itself. Is time an illusion?